Many natural phenomena follow the law that an amount A varies with time t according to the function a of t equals a sub naught e to the kt, where a sub naught, this thing here, is our initial amount. If k is greater than 0, we call it a growth equation. If k is less than 0, we call a decay equation. Here, the size p of a certain insect population at time t, which we measured in days, obeys a law of uninhibited growth. In our formula, p of t equals 500e raised to the 0.02 t. So we're going to determine the number of insects at t equals 0. So we're going to have p of 0. And that's going to be 500e to 0.02 times 0. So we're going to take our amount and we're going to plug it into our calculator, let it do the work for us. So 500 second ln 0.02 times 0. So when we put that in, we're going to get 500. Which again makes sense because the number that's in front of e is our initial amount. And since 500 is in front of e, it makes sense that when we plug in 0 for t, we only get 500 back. So knowing this, what is the growth rate of our insect population? Our growth rate is k. And k is the number in front of t in our exponent, which is 0.02. But we want the growth rate, so we're going to take our 0.02 and we're going to multiply it by 100. And we can say that our growth rate here is 2%. So what is the population after 10 days? Don't know. But we do know that time is 10. So we can plug 10 in for t and let it tell us. So p of 10 equals 500e to the 0.02 times 10. And here we are going to just let our calculator do the work for us. So 500 second ln 0.02 times 10. And it gives us 610.7. Now, I don't know if you've ever seen a decimal portion of a living creature, but you can't have that. So we're going to always round down to the nearest whole number because we want a whole creature. There's no such thing as 0.7 of an insect, at least not a living one. So we can say that there's 610 insects in this population. Now, when will the insect population reach 800? Well, since we're trying to find time, that means we need to know what p is. So, logically, it makes sense that 800 is p. So I'm going to set my equation equal to 800. So 800 equals 500e to the 0.02 t. And now I'm just going to solve. Divide both sides by 500. And when I reduce it down, I'm going to get 8/5 equals e to the 0.02 t. Then I'm going to take the natural log of both sides. So I'm going to have ln of 8/5 equals, and I'm going to skip a step here, and I'm just going to say this is 0.02 t because ln e is just going to go away. And then I'm going to divide both sides by 0.02 to solve for t. So I'm going to have ln of 8/5 divided by 0.02 is going to be my t. But I need to know the time, so let's put it in our calculator and find out. So ln of 8/5, make sure to close parentheses, divided by 0.02 is going to give us 23.5. So time here again is measured in days, so 23.5 days. And finally, when will the insect population double? Well, to double, you need to know what its initial amount is. And we know from part A, it's 500. So I'm going to set the equation equal to 1,000 because double 500 is 1,000. And I'm going to do the exact same thing I did before in the previous part, solve for t. So divide by 500, and I'm going to get 2 equals e 0.02t. Now I'm going to take the natural log of both sides, so ln2 equals 0.02t, and I'm going to not write in the ln e because again it goes away. Divide both sides by 0.02, so ln2 over 0.02 is going to be t. Now what is that in time? Well, turns out that's going to be ln2 divided by 0.02. It's going to be 34.7 days. So that's how long it takes for this insect population to double.